Hello and welcome. In this video, we're going to talk about what a power series is and how we can use a power series to represent a function that is maybe not so friendly as a geometric series so that we can work with it in different ways in future sections. So we're going to start with what is a power series. We're going to talk about the relationship between a power series and a function, and then we're going to work through some practice problems where we rewrite a function as a power series and find the interval over which those two are the same. So let's go ahead and jump in. So remember, in the last video, we talked about what a power series is. A power series is an infinite series whose pieces are expressions in terms of a variable with an increasing power. So like a polynomial, except a polynomial has to have a defined degree. And if we're talking about a series that's going to the power of n, an infinite series, then it won't actually have a degree. So we're sort of talking about a polynomial, but really we're talking about a polynomial-like expression. So we talked about the general form of a power series, a geometric power series, which is centered at C, so A being the first term, which would be what we get if we plug in n equals 0, times x minus c, so x minus the center value, to the power of n. And if we expand that out, this is the expression that we would get. So here we have our general term. Here we have the first term, the second term, the third term, the fourth term, and so on. And we can see that this is infinite over here because we have this plus dot, 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 this ellipses going on to infinity. If it happened to be that the polynomial was centered at 0, then each of these terms would just become x instead of x minus some other value. So why is a power series useful? And we know we talked about finding the interval of the convergence in the last video, but why is a power series something that could help us? And the idea here is if we had a function that was maybe hard to work with, but we needed to use that function to approximate something, to estimate something, to model something, it might be more comfortable if we could rewrite that function as something that looks an awful lot like a polynomial, but still analyze the behavior as we go to infinity. So a power series is a helpful tool that allows us to work with something that we are more comfortable with, a polynomial. So let's actually look at a function that's maybe not so friendly and try and find a way to represent that function using something that we are more comfortable with. So let me see if I can pull up a graph here. So here graphed to the right, we have the function 1 over 1 minus x. And what we want to do is see if there's a way that we could represent this function as a series, as an infinite series. So something I want you to notice is that this looks really similar to a formula that we're pretty familiar with. And that formula would be 1 over 1 minus r. So if we were looking at that formula, which is the infinite sum of a geometric series, maybe we could find a way to relate this to that series. So we know that a geometric series is of the form a times x to the power of n, or r to the power of n. We're going to use x in this case. And we know that when, based on this graph, if we're trying to model using this same graph, we know that when x is 0, we have 1. So I'm going to just get rid of a, and I'm going to look at the sum from n equals 0 to infinity of x to the power of n. And let's actually just look at the first few terms. So if I plugged in 0, I would get 1. If I plugged in 1, I would get x. If I plugged in 2, I would get x squared. And let's just stop there and let's see what would happen if we graphed the function 1 plus x squared in relation to what we're looking at. So let's go ahead and add that graph in there and see if these look anything alike at all. So here we have both of those things graphed. And if we just, at first glance, they look nothing alike. We have a quadratic, we have a rational function, but if we zoom in, there's definitely an area where they look really similar. And I'm going to zoom in even more. Whoops, I didn't mean to zoom that. Let's move this over. There we go. If I zoom in even more, there's definitely, I would almost say that sort of from here to here, they look really similar. And we're just using the first 3 terms of this series over here to represent that function. And I would say not over a large interval, but over a small interval, I can't tell you where the blue stops and where the red starts. Well, what would happen if we actually just added another term? So if we go into here, the next term in this series would just be plus 1 x to the power of 3. Oops. X to the power of 3. Well, now it looks even more similar. Well, what happens, and you may start to see where I'm going here, but if we add another term, x to the power of 4, this looks even more similar. And it almost seems like the interval might be getting slightly larger here. So I want you to notice this blue quartic-looking function, now that we've extended it out, is a good representation over a small area. I would say maybe from here to here, it's a pretty decent approximation. But just like with local linearization first semester, as soon as you get past that to a certain point, it is no longer a good representation. I would not plug in a value into this blue function to approximate what's happening when x is 5 or when x is -2. This function and this series don't behave in a similar way unless we're in this small region. But we could say that if we went to infinity over some interval, this function is equal to this infinite series if we kept going on to infinity. And that's a really cool concept to be able to even wrap your head around. Over some small interval, instead of having to use the function 1 over 1 minus x, we could represent that as an infinite series, or even if we're really close to x equals 0, part of an infinite series. And it would be much easier to plug values into this function. It would be much easier to take the derivative of this polynomial, and that could come out to be really helpful in a lot of different circumstances. So let's formalize a little bit more what we just kind of noticed in this picture here. So again, what we're saying, or what we just showed visually, is that over the interval, that's not the highlighter, over the interval of convergence, these two things are equal. And that's just really kind of a unique, interesting, hard to wrap your head around idea. Over some interval, we can say that this function 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the power of n. This is so cool. So this is our first jump into the idea that we could actually talk about an infinite polynomial or an infinite series that is exactly equal to a more complicated function. And how we came up with this was starting with the idea of having the formula for an infinite geometric sum and talking about how we could represent a function as that infinite sum so that we could rewrite it using series notation. And that's what we're going to explore in the rest of this section. If we are given a function, can we rewrite it using this logic here to make it look like a geometric power series? And then can we find the interval over which this series is a good representation of the function? Can we find the interval of convergence? So let's look at some examples and work through these problems together. Okay, so here we're going to find a power series for the following function. We're going to write it using sigma notation, and we're going to expand it out, sort of like we saw in the sum at the beginning of this section of notes, so that you can see all the different ways. You can just get a better visual idea of what's going on there. Then we're going to find the interval of convergence for each of these series. So my goal here is to be able to rewrite this function in the form 1 over 1 minus r. Because if I can do that, or even I'm actually going to say some number over 1 minus r, because if we can do that, then we can identify what our first term is, what our a value is, and what our r is, which means we could rewrite it from n equals 0 to infinity of a times x to the power, I shouldn't say x, but r to the power of n. So if I manipulate this function that's here, and I needed it to be 1 minus something. I'm asking myself, what would give me positive 2, because this is supposed to be positive 2. Well, I'd need a negative 1 here, so that if I distributed that negative sign, I would end up with 2. And I need to be able to distribute this negative sign to get a positive x, so I also need a negative x. So I'm manipulating what is here to make it of this form, 1 minus r. So now I can actually tell what my r value is. I kind of want that to be in a different color, negative 1 minus x. So then from there, now that I rewrote it this way, I can rewrite it as a sum. So I'm looking at the sum from n equals 0. The first term is the numerator there. So 1 times the ratio, which is negative 1 minus x, to the power of n, which you could simplify this a little bit. You don't need the 1 there. If you feel more comfortable, you could rewrite it with your x in front. But if I was going to expand this out, the first term is 1. It better be 1 because that's what it was here, plus negative x minus 1 to the first power, plus negative x minus 1 to the second power, plus negative x minus 1 to the third power, plus dot, 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 plus negative x minus 1 to the nth power, plus dot, dot, dot. So this is just expanding out the series by listing, and it asked us to say the first 4 terms and the general term of the series. Now that we have a series and we know that it's geometric, we can find the interval of convergence, right? We can say that the absolute value of the ratio must be less than 1. So we can set up an inequality to solve. If I add 1, I'm going to get here. And if I divide by negative 1, I'm going to get here. And remember, since this is geometric, we don't need to check the endpoints. This is my interval of convergence. So again, we're taking the function that's there and rewriting it so that it's of the form 1 minus r, so we can identify what r is. The numerator, so the part that's above your 1 minus r, is going to be your first term, and then we can expand out the series and find the interval of convergence. So let's go ahead and look at b. I'm going to give us a little bit more space to do that. Here we go. So this is already in the form 1 over 1 minus r, or a number over 1 minus r. So I can say the sum from n equals 0 to infinity of 5x to the power of n would represent this function over some interval that we haven't yet found. But if I was going to expand this out, 1 plus 5x squared plus 5x to the third plus dot, 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 plus 5x to the n plus dot, dot, dot. Notice I'm not actually multiplying anything out. Writing it in this way is all you need to do. Expanding it out more might just be confusing. So, or a waste of the time that you need to use on other things. So anyways, just leave it in this form. If you really want to simplify some of it, you can, but it's just not a good use of your time. This will converge when the absolute value of the ratio is less than 1, which is going to be from negative 1/5 to positive 1/5. So what we can say is this infinite series is equal to this function on the interval from negative 1/5 to positive 1/5. As soon as we go further away, these two things are no longer equal. But as long as we're staying close or within the bounds of this interval of convergence, these two things are equal. This series is equal to this function. Okay, let's look at some more practice problems. Okay, so same setup. Let's try and rewrite this as 1 over 1 minus something. Well, if I need the denominator to stay as just negative 2x, I need to get rid of the 1 that I just created that wasn't there before. So if I distribute right now, I get 1 minus 1, which is 0. I also need it to be negative 2x, so I need a positive 2x here, so that if I distributed this, I would end up with just negative 2x once I simplify. Now that I've done this, I can identify my first term as 1 and my ratio here, so I can write the sum from n equals 0 to infinity of, I'm going to write this as 2x plus 1 to the power of n, and then if I'm going to expand it out, that's 1 plus 2x plus 1 plus 2x plus 1 quantity squared plus 2x plus 1 quantity to the third power plus dot, 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 plus the general term, 2x plus 1 to the nth power plus dot, dot, dot. Now, if we were going to find the interval of convergence, we're going to take the absolute value of our ratio. It needs to be less than 1. So -1 is less than 2x plus 1 is less than 1. If I subtract 1 everywhere, I'm going to get here, and if I divide by 2, -1 is less than x is less than 0. This would be our interval of convergence. I want you to ask yourself, just quickly to review something else from our last video, what would the radius of convergence be? Well, halfway between -1 and 0, or the distance from -1 to 0 is 1, so half of that would be 1/2. So if you were asked about the radius of convergence would be 1/2. Okay, number 2, if we are rewriting this, and actually this one works out pretty nicely. The only thing that we need to do to see this better would be to write this as 1 minus -2x. So we could say the sum from n equals 0 to infinity, and I'm always starting with n equals 0 because I'm always going to have this be my power. I'm not going to have n plus 1 or n minus 1. If you want this to start at 1, if you want the index to start at 1, you're going to have to manipulate your exponent so that you get the first term being 1. I like to just start at n equals 0 so I can have whatever this be 1, which in this case is my first term. So I'm going to write the ratio in here. This is equal to 1 plus -2x plus -2x to the second power plus -2x to the third power plus dot, 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 plus -2x to the nth power plus dot, dot, dot. And then if we were finding the interval of convergence, we're looking for when the absolute value of -2x is less than 1. So when is -1 less than 2x less than 1? That's -1/2 less than x less than 1/2. So for all values between -1/2 and +1/2, this series is equal to this function. The series converges to be the same as the function over that interval. And this radius of convergence, if we were asked about it, would also be 1/2. The distance from -1/2 to +1/2 is 1, and half of that distance would be 1/2. Let's go ahead and look at 2 more examples and then wrap up. All right, and I'm actually going to change example 4. I want to have another one where there's a different value in the top. So I'm going to make that a 4. So here on number 3, the big difference is that the first term here is 5. So when I'm writing my sigma notation, I'm going to have a 5 times something to the power of n. That 5 is the first term. The ratio here, if I rewrite 2 minus x to be 1 minus, this is going to be -1 plus x, or x minus 1. So I'm going to rewrite that as x minus 1 here. And then if I expand this out, I'm going to have 5, which is my first term, plus 5 times x minus 1. Every single one of these terms is going to have a 5. So make sure that you don't forget it, because it should be in front of every single term. 5 times x minus 1 to the n plus dot, dot, dot. This is going to converge for x minus 1 less than 1. So -1 is less than x minus 1 is less than 1. So 0 is less than x is less than 2. What would the radius of convergence here be? The radius of convergence would be 1, because the full length from the interval of convergence is 2. So half of that is 1. So things to be cautious of. This is the first one where we have had a first term that isn't just 1. So that's going to manipulate this a little bit. Actually, I'm going to change, I can't make up my mind. I'm going to change number 4 to have an x in the numerator. So I'm going to rewrite this as x over 1 plus x. So now, and I'm going to do my work for number 4 down here. Now, a is equal to x, and r is equal to -x. That means that we have the sum from n equals 0 to infinity of x times -x to the power of n. And yes, you could simplify this. This is the same thing as the sum from n equals 0 to infinity of -x to the n plus 1, since this has a power. You don't have to simplify it in that way, but you can. So that would be equal to, the first term is x plus negative x to the first power, to the second power, plus negative x to the third power. You could also rewrite this as an alternating series, plus negative x to the fourth power. Oh, I don't know why I did that term. That's okay. Plus negative x to the nth power. N. Yeah, that's fine. Or n plus 1 plus ... So now I have written this as an infinite series. This infinite series is going to converge when the absolute value of negative x is less than 1, which is just going to be for all values between negative 1 and 1. So this would have a radius of convergence of 1. So to recap what we covered in this video, we talked about what a power series is and why it's helpful. That a power series can help us represent a function that maybe isn't so friendly using a polynomial-like series that allows us to approximate, estimate, graph, look at things in a much easier way. We focused on a geometric power series and how to manipulate a function that maybe looks like 1 over 1 minus r, the form for an infinite geometric sum. How to manipulate a function to look more like that so that we can express it as an infinite series and therefore represent it as a polynomial-like series or as a power series. We talked about how those two things, the series and the function, are equal over some interval of convergence. So we reviewed that idea as well. And how we don't have to check the endpoints for those because this is a geometric power series that we're writing. So it will never converge at the endpoints. And then we reviewed that the radius of convergence is just half the length of the interval of convergence. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.